Well, how's everybody doing out there? Well, welcome to day 28 of Corona Online School and the last lessons of the semester. So, good job hanging in there up until this point. So, today what we want to talk about is actually testing the significance of our regression equation. So, the one downside is the way we are kind of going about this. We find the regression equation, which well, we don't necessarily know whether it's a good regression equation or not. And so that's kind of what I mentioned up here above that basically, given any set of data, we can always find a linear equation to try and model that data. But whether the data is actually going to be any good or not is a different question. So, because if it's, if our R value is near zero, it's, yes, there's a line, but it doesn't mean it's actually going to do a really good job of predicting other values, which is really the whole point of a linear regression to begin with. So in this case, what we're going to do is do a hypothesis test to try to test and see whether our correlation coefficient is significant and whether we're going to have a good linear regression or not. So there's a couple new symbols we're going to use for this hypothesis test. So in this case, the population correlation coefficient that we're going to use is the Greek letter rho, which is that P looking thing. And then our sample correlation coefficient we know is R in this case. So P, of course, or rho is always going to be unknown. And R is going to be known because we're going to calculate it from the data. So the test statistic that we're looking for, oh, and I guess I forgot to mention up here, since in this case we're always looking for the extremes, because remember the good values that we're interested in are the things that are close to 1 and close to -1. So if we're near 0, that's kind of the bad thing in this case. So what we're going to be looking at are just whether rho equals 0 or rho is not equal to 0. So we're looking for something that's significantly different than 0. So it doesn't matter whether it's low or high, those are both good values for us. We just don't want it to be anywhere near 0. So we don't have to worry about less than, greater than, any of that stuff. So our hypothesis testings are always going to be equals, not equals situation. So our test statistic is given by the following formula, where R is going to be our correlation coefficient and N is our degrees of freedom. So in this case, notice our degrees of freedom are N minus 2, and that's just because we've got a two variable situation going on in this case, because we've got our X's and our Y's. But all we need is just the R and the degrees of freedom to be able to calculate our test statistic. So in this case, our p-value, the graph is always going to look like this because, again, it's going to be a two-tailed test since we're using the equals, not equals situation. So we can calculate our alpha using our t method that we did before. So in this case, this is everything. This is going to be a t situation. So we can use inverse t, our alpha over 2, comma the degrees of freedom, to figure out what these values are, and then we can use those as a way to compare against our test statistic to see whether we fall in the blue region or not. So again, a lot of the same stuff we've been doing with the other stuff. So finally, here's a little summary like we've been doing for all the other hypothesis tests we've been doing. So again, degrees of freedom are N minus 2 because of the two variables. So again, step 1 is always state the hypothesis. So in this case, again, this is always going to be exactly the same. So the null hypothesis will always be the population correlation coefficient is not significantly different from 0. Or in other words, there's not a significant linear correlation between X and Y in the population. And the alternate hypothesis will always be that the population correlation coefficient is significantly different from 0. So that means it's going to be either on the upper end or the lower end of our graph. In other words, there is a significant linear correlation between X and Y and the population. And that way it'll make a good model. So again, in symbols, this is going to be H naught is rho equals 0. H1 is rho's not equal to 0. Again, we want to calculate our test statistic, which is the same as before. Calculate our p-value. So again, in this case, since it's a two-tailed test, we're going to do 2 times the t-CDF. In this case, I put absolute value of whatever, because if our t-value is negative, then that means we're going to be down in this area somewhere. Or if it's positive, it's going to be up in this area. But technically, if you just take the absolute value and do comma 100,000, then that way you don't have to worry about whether it's an upper or a lower. You can always just kind of calculate it as an upper, and it'll work the same either way. So again, if our conclusion's always the same, if p is less than alpha, we reject the null hypothesis, so that means that's good. That means there is a linear correlation, or in other words, the two variables are dependent. P is greater than alpha, we fail to reject the null hypothesis. There's no evidence that the two variables are independent, so even though we've got a linear regression line, it's not going to be a very good one. It's not going to make good predictions, which is what we're really interested in for a regression line. All right, so let's take a look at an example. So again, these are the same examples we've been working on kind of throughout the whole section. So this is the home price one. So using an alpha of 0.05 significance level, test the claim that there's a linear correlation between the selling prices of homes and the square footage of the homes. And so this is the same R value I found before. I forgot to type it in here, so I just wrote it from a previous classwork packet. So again, first thing we want to do, state the hypotheses. So just rho is equal to 0. So H1 is rho is significantly different than 0, so not equal to 0 in this case. So calculate the test statistic. So again, remember in this case, the alpha that we're interested in is going to be alpha over 2. So when we're looking at 0.05, we want to divide that by 2. So that's going to give us 0.025 on this end, 0.025 on that end. So when we're trying to figure out these t values, we're going to have to use inverse t. And so we can use the lower end, like that's totally fine if we want. So we can do, how did I write it up here? Let's see. So it's, yep, that's right. So I can just do the lower end, and it's going to be opposite on the other side. So I can just do 0.25, and then our degrees of freedom are going to be the n minus 2. So in this case, our n is 1, 2, 3, 4, 5, 6, 7, 8. So our degrees of freedom are going to be 6 in this case. So our inverse t, so let's go ahead and find that first so we can figure out what these t values are associated with these alphas. So go to graph and calc. So second vars. So inverse t is number 4, 0.025, comma 6 for our degrees of freedom. So it looks like in this case it's going to be negative 2.45 is going to be our t value. And so the upper is just the opposite, so it's just going to be positive 2.45. So now that we've got that, let's go ahead and calculate our test statistics so we can compare it to these two values. So again, our t is just, in case you forgot, r times the square root of the degrees of freedom, all divided by 1 minus, or the square root of 1 minus r squared in this case. All right, so in this case we've got t equals 0.90059, square root of 6, all divided by the square root of 1 minus 0.90059 squared. So let's type this in the calculator real quick. It's 0.90059 times the square root of 6. So that gives me my top number, and then divided by the square root of 1 minus 0.90059 squared. All right, so it looks like our t value is going to be 5.08. So our t is 5.08. So in terms of our picture then, that means this guy's going to fall somewhere up in this area, or maybe even further up. So what do you think? Does it, just by looking, does this look like it's going to be a fail to reject or a reject? Yeah, so this looks like it's going to be a reject H naught, but I like to check ourselves. So let's also go and do this on the um, TCDF as a way to do this. So in this case, what we're going to do is 2 times TCDF. So in this case, our value is already positive, so we don't have to worry about, doing the absolute value. 100,000, comma, our degrees of freedom, which were 6. And so again, let's do this in the calculator. And if you want, you can do it all in one step. If you want, if you want to do the 2 times first, or if you want to do the 2 times afterwards, it doesn't matter. So second vars TCDF was number 6. So we had, what was it, 5.08, comma, 100,000, comma, our degrees of freedom, which was 6. So even without multiplying it by 2, we're already less than 0.05, but let's go ahead and really make it look good here. So by 2, so 0.022 is our p-value. So this is our p-value, which is going to be 0.00. I think that's right. I think I got the right number of zeros. Let me. Oh. Yep, that's good. All right. So 0.020. So now let's draw our conclusion. So in this case, so this is definitely less than our alpha. So since p is less than alpha, there is sufficient to prove that the 2 variables are dependent, or in other words, there's significant evidence to prove this is a good regression. All right. So again, not too much different than any of the other hypothesis tests we've been doing. So I've got the same ones you guys have been working on in practice. So go ahead, stop the the video's getting ready to end anyway. So work on these guys, and then when you're done, come on back and we'll head on over to 12.5. Good job, everybody.